Okay, are you guys ready? Everybody ready? Good to go? Y'all are going to need to write these parts down. I'll try to keep it as short and sweet as possible. But give me a workaround. We're engineers, we're not physicists, so we're going to try our best to make this as quick and painless as possible. But we do need to know like what work is. So what does work mean? Okay, work can be physical labor, but in an engineering sense, work can be something else other than physical labor. Because think about it, like, okay, that's fair. Yeah, you have to have some kind of oomph to do work, exactly. There has to be some kind of force involved. Okay? If you're going to make something move, you have to do work on it. Okay? And that's really what happens. If you're going to make something move, anything, if anything is going to be able to move, you're going to have to do work on it to make it move. Okay? So work is essentially spending energy. Okay? So work, I'm just going to call this spending energy. Okay. Yeah. And whenever you spend energy, the formula for work is you're going to need two things. You're going to need a force and you're going to need a distance. So it's force times distance, which means this one is a little bit tricky to actually find work this way because that means we would need a force sensor or we would need to know the weight of the object, which is why it's really nice to use the winches because if we're looking at the weight of the objects, that's the force that we're working against, okay? So if you're pulling up with the winch, that means that you're trying to fight against gravity, okay? So this force can be a lot of different things. This can be a weight. This can be force from an engine or motor. Let's see here. Is there anything else? I think this is the big three that we're gonna deal with. So like if it's got the actual natural weight of the object is a force in itself. An engine, if we hook it up to something, can provide a force. A motor can provide a force. And I think distance is pretty self-explanatory. I don't think I have to explain to you guys what a distance is. You have no clue what a distance is? Okay. Well, you really want me to go into like the what is reality? Like you want to go like super deep? Sorry, this is engineering class. We don't do that. Um, we just take it for face value and move on. Okay. Now, the energy, the spinning energy, the work is measured in joules, and we're gonna try to stick with metric, just because it's simply easier to do. Metric is really, really nice in the calculations. The English units don't really work out so nicely, and it's not really even used that often. It is used in several like niche cases, but another way to write this formula is you could write it this way because we know that force from ninth grade, we know that F is equal to ma. So you can also say that work makes you mad because it's mass times acceleration times distance. For for us, the force times distance is probably easier because we can just use a force sensor to measure what the force is. Um, the mass times acceleration times distance becomes a little bit more useful in physics because acceleration due to gravity is a thing. We don't really mess with it that often. The only time we use it is for like weights and stuff like that. But both of these are kind of important to know. Okay. Now, energy, the difference between work and energy, they're really closely related to each other. Okay, so work is just how you would actually spend said energy. So work is like a process. Energy is the ability to do work. Kind of like the weekend. Just because you can do work doesn't mean you are going to do work. So the difference between work and energy is work is an active process of spending energy in one way, shape, form, or fashion. Energy is just the ability to do so, which means that you can take energy and you can store energy. You can't take work and store work because work is an active process. But you can take energy and you can store energy. Okay. The easiest example of taking energy and storing energy is taking like a mass and just lifting it up in the air. Okay. By lifting something up in the air, you are storing gravitational potential energy because if I let it go, what's going to happen? That energy is going to get spent. Okay. The work that because think about it, it takes work to be able to take this and move it up. So if I take the cone and I pick it up from the table and I lift it up into the air, this is taking work to do. Why? Because I'm moving it. Anytime you move something, it requires work. So whenever we take our winches and we lift up the mass into the air, guess what we're doing? Work. Okay. We are doing work. Okay, we are spending energy. And more specifically, we're taking that energy and we're storing it. There are a crap ton of different types of energy, and I was supposed to teach you guys all about energy, but this year being the way that it is, I have skipped all of the stuff that we have not needed, and I'm saving that for if we go digital. Okay, so this is either going to be a really, really boring end of the year, or when we go digital, I'll teach you guys all about the different forms of energy. Okay, so just keep in mind now that energy is the ability to do work, and that work is like actually spending energy. If you want to talk about power, power is our energy over time. So it's how much energy you can spend. So energy spent over time. Gee, I really thought I just talked about like what it is whenever you talk about energy being spent. Isn't that the same thing as work? No, not the same thing. Energy spent. It's like right there. It's in like, but it's highlight. Let me highlight this. It says spending energy, right? It can't be the same thing. Okay, so if you take your work, the work that you do over time, so you're not going to hear me say energy spent over time. You're going to hear me say work over time. And that's the way that I'm going to do it. Okay? Work over time. Um, Now, so you can actually find out how much work we're going to be doing over a specific amount of time, and that will tell us our power. Okay? There's another way to do this, though. If you're dealing with electrical components, you can use a different formula. So instead of doing P is equal to work over time, that one's important. Another way to do this from an electrical standpoint is P is equal to IV, which is going to be current times voltage. Okay, let's talk about the units here. The voltage is measured in volts, the current is measured in amps, and the power is measured in, think light bulb. Think, think light bulb. Watts. Watts. Okay, watts. You never heard of like a 60-watt light bulb? Okay. So power is measured in watts in this case. And if you do work over time, you also get watts as well. But the difference is the work in the top equation is measured in joules, and the time is measured in seconds. Okay. You can't. There's no such thing as unlimited power because that means that you would have to have an infinite amount of energy. And I guess you could just spend a bunch of energy in zero time. I guess if you divide by zero, things explode. Since power is work over time, if you do something in 0 seconds, which makes absolutely no sense because you can't do something in 0 seconds. You can't just instantaneously teleport from one spot to the other spot. So yeah, y'all are trying to be physicists. You're not trying to be engineers. Just just go with it. I don't know. You know what? Maybe that is an engineer thing. If I say you can't do that, maybe it is the engineer motto to be like bet. That might be what y'all do instead. So I don't know. I don't. You wouldn't like if you stopped time, you wouldn't know. If time stopped for like 5 years between every second, you would have no idea because time stopped. I don't know. It's weird. Kind of, yeah, but that's not that is totally not within the realm of engineering. So Totally not. All right. No, we're not. This is engineering class. I only have enough trauma for one day. Magnets are not infinite energy. Magnets are a different thing altogether. So let's say like you've got your winches and you've got your mass down here, and whenever you pick it up, what you're going to be doing is the distance that you're going to use to measure is going to be how far it actually rises up into the air, and the force that you're going to use is the actual weight of the object. So the weight of the object in newtons is what we're looking for. Okay, y'all should have gotten both of those Friday. So we should have like we should have everything. We should have the weight of the mass. We should have the time. We should have the current and the voltage. I think we got all of those done before we left Friday. So what we're going to do is we're going to look and compare these two powers to each other. We're going to do the power equals work over time because we can find the force times distance, and we're going to do the P equals IV because we have the current, we have the voltage, and we're going to see how those compare to each other. Okay, does that make sense? Do you think that they're going to be the same? Why not? We'll go out there because I mean, like think about it. Like one of them, you're just taking a weight and you're lifting it up and you're measuring a time, and the other one is you're measuring the current and the voltage going through the motor. So you think they'll be different? Now you changed your mind now on me. What'd you change your mind? You said they were going to be the same. Oh, you said they're not going to be the same. Okay, so it didn't change your mind. That's okay. So they're not. So they're not going to be the same. Why not? Okay, but you gotta have some kind of reasoning. Like, why are they not the same, or the two power things? Okay, so we know that work is force times distance. We have the force. We've got the weight of the object, and we've got the distance that it travels, and we know how long it took. So we've got the time as well. We also have the current and the voltage going through the circuit. So we have two different ways to find the power of this winch. Are we going to get the same number? Theoretically? Okay, so like theoretically, yes. Let's test it. Let's find out. Okay, right? Yeah, that's all of us. It's all of us dumping stuff on you at the same time. Welcome to the new digital age. And then it goes, yeah, and there it goes. All right, so that's what we're going to do. We're going to try to calculate these two power ratings. We're going to multiply. We've got all the information. We're going to get those power ratings, and then we're going to compare them to each other. Okay? We're going to compare them to each other. So we have the time for a 15-second interval. Um, so let's just go ahead and work with that. So, or no, 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 I'm sorry, a 15 centimeter interval. So we'll work with that and we'll see how it goes. So that's what we're going to do right now. We're going to take a little bit of time to do that and go. It's mathy time. Digital people, this is what we're working on. So I'll provide a video of the data.